Okay, this is quantitative homework number 5. In this, we're going to use some of the previous skills that we've learned, but instead of doing back testing or something like that, we're going to run regressions and then decide whether the regressions give us a good model or not. So I've already set up most of it. I'll leave the setup up to you because you should know how to do that by now. So download the data for all 3 variables. I did that here. Instead of using his companies again, I decided to do my own thing. So I downloaded sugar and water as our independent X variables and Coca-Cola as our dependent Y variable. So we'll see how the returns of sugar and water have affected Coca-Cola over time. So I set all of that up with our adjusted close and our weekly returns. Split the data into 5 years in sample and 3 years out of sample. I've done that as well. And run the regression between Coca-Cola and the index you picked using the in-sample data set. This will be called Model 1. And then run the regression between Coca-Cola and both indexes I picked using the sample data set. This will be called Model 2. So we're going to be working with in-sample for now. Our first model is going to be a simple linear regression between Coke and water. And our second model is going to be a multiple linear regression between Coke and water and sugar. So let's start with our first one. Go to data, data analysis, and regression. And for our, I'll just delete all these. Okay, for our input Y range, which is our dependent variable, we're going to be using Coke. And for our X range, which is our independent variable, we're going to be using water. Okay. Now we want to have it show us confidence level. We'll take the output range. We'll pick that to be right here so it doesn't go in a new sheet, and we want to see the residuals as well. Okay, so that'll give us our first regression. It tells us all kinds of fun stuff. And let's do our second regression, the multiple linear regression now. Again, let's run a regression. Our input Y range is going to be Coca-Cola, that's already selected. And this time our input X range is going to be both water and sugar. We're going to select both because we want 2 independent X variables. Confidence level, output range, residuals. Our output range, we want that over here. And let's do it. Let's see what it gives us. Okay, so we have 2 different regressions run now. And the next instruction is, are the regressions statistically significant? So the way that we can see that is by looking at the F and at the p-value of the F. So we can see that our alpha we know is 0.05 because that's the standard. And our significance, our p-value is way smaller than 0.05, so model 1 is significant. And over in model 2, also our p-value is way smaller than 0.05, so model 2 is also statistically significant. Okay, so that's a start of something. Now, what was the next question? Which model is better? How much of the variation in Coca-Cola's stock return is explained by that model? Okay, so when we're working with 2 different regressions that have different numbers of X variables, this one we only have 1 and in this one we have 2, we can't look at our normal R squared to tell us about which one is better. We have to look at our adjusted R squared to tell us which one is better. So our adjusted R squared of model 1 is 0.200. And our adjusted R squared of model 2 is 0.201. So we can see that model 2 is a little bit better at predicting Coke's price than model 1 is. And our R squared will tell us exactly how much of the variation is determined by our variables that we picked. And it's about 20.78%. So that answers that question. So again, the adjusted R squared is used to compare between the 2 models when you have different numbers of X variables. Okay, I keep going back to that page by mistake. So that explains this question. I'm just going to get rid of this actually. That explains that. Now number 7, are the coefficients of both models significant? So again, significance for coefficients can be determined from p-value just like everything else. Let's look at our first model. We have our intercept and the p-value is higher than 0.05. So we will say that the intercept is not significant for model 1. But for the X variable, the p-value is much smaller than 0.05. So we can see that our X variable, or the coefficient for our for water, right? The coefficient for water is significant. Now let's go look at model 2. So the intercept for Coca-Cola, the p-value is above 0.05, so we're going to say that's not significant. The X variable coefficient for water is way smaller than 0.05. So we're going to say that that is statistically significant. And the X variable 2, the coefficient for sugar, is 0.22. That's bigger than 0.05. So we're going to say that that's not statistically significant. So it looks like the most significant thing we have in our models is our water prices, or our water returns, and how those affect Coca-Cola. Okay, next question. What's the effect of a 1% change in the, let's say, in the water index return on Coca-Cola's return? Okay, so first we can look at our model 1. We know that this coefficient is determines the slope of this of water's movement. So if water will change 1 unit, then Coca-Cola will change 0.36 units. And over here we can see as well, if water will change 1 unit, Coca-Cola will change 0.35 units. So that also didn't change very much even when we put sugar into the mix as well. So that answers that question. What this is essentially asking you is what happens when there's a one unit change in X to Y, and that's the slope. So that is exactly what that is. Okay, so check the hypothesis that the beta of the gold index in model 2 is greater than 0.5 at a 5% level of test. So that means alpha of 5%. So we're looking at model 2. And we have to do a hypothesis test on the coefficient. Now, we haven't done that in our homeworks yet, but this is on the formula sheet. There is a way to do a hypothesis test of coefficients. I did have, oh, I guess I got rid of it, but that's okay. This is the formula. So you're going to take your, here, well, actually, we need to do a little bit of setup first before we do this. Let me get out my handy dandy formula sheet. Okay. So, as we can see, we can do hypothesis testing on the coefficients for multiple linear regressions. So, the first thing that we need to determine, where the hell did this go? The first thing that we need to determine is our degrees of freedom. So, we need to know our T, we need to know our K, and we need to know our degrees of freedom based off of that. So, T is the total sample size, right, which is 256. K is the number of X variables we're using, which is 2. And so our formula for degrees of freedom is T minus K plus 1. And that gives us, oh, my bad, I wrote K instead of doing that, that was my bad. So that gives us our degrees of freedom, and we can see you get the same residual degrees of freedom here. So now for our T test stat, what we're going to be doing is, oh, hang on, let me also set up that our alpha is 0.05. Okay, we're going to need that. So our test stat, right, just like every other hypothesis test, we have to have a critical value and a test stat to test it against. So first we could do our critical value. We know that's going to be T dot inverse because we're doing a right-tailed test. Right? It's asking us, check the hypothesis that the beta of the gold index or Coca whatever index is greater than 0.5. So we're doing a right-tailed test, right? So we're going to do our probability 1 minus 0.5 because it's on the right side, and our degrees of freedom we have. Okay, so that's going to be our critical value. And our test statistic is going to be, we have our beta that was returned. What are we testing this for model 2? Yeah, we have our beta that was returned by our, let me put this in parentheses. We have our beta that was returned by our regression. We have that minus the original beta that he's asking us about, which is 0.5. That's in the question, right? You have, check the hypothesis, beta of gold greater than 0.5, right? So we're testing it against beta null, which is 0.5, and that's all divided by the estimated standard error, which is given to you. You're not going to have to solve that, so that'll be given. And that's our test statistic. So since it's a right-sided test, we need to see something that the test statistic needs to be greater than our critical value in order for it to be rejectable. And we can see that our test statistic is much smaller than our critical value. So no, we would not reject this hypothesis at an alpha of 5. I'm sorry that was a little, I was like writing that down while I was doing it. I hope that was clear. But again, super easy formula to use, super easy formula to use. You just have to know when you're making a critical value, if it's a right-sided test, you're working with alpha of 0.5, you're going to do 1 minus alpha in order to get the rightmost part of the distribution. And again, degrees of freedom you calculated. Okay, all of that is done. Now the last part. Calculate the RMSE, which is the root mean squared error of both models in the out-of-sample dataset. Which model is better? So when we're looking at RMSE, we want to get the lowest RMSE possible because it's the lowest amount of error. So again, I already set up our out-of-sample with all of the returns and everything. Now we have to come up with the predicted value of model 1. And the way that works is we simply we're just going to build a linear formula. We're going to go to the in sample and we're going to go to model 1. We're going to take our intercept. We're going to lock that in. And then we're going to add our x variable and lock that in and multiply it by our first x. Okay, why is Excel being all weird? Hold on 1 second. Sorry. Plus our first x coefficient. Right, lock that in, and then multiply that, there we go, by our first x, not locked in. So essentially what you just did is you just did literally y equals, hold on 1 sec, why is this being weird? Hold on. Okay, 1 sec, this just got all messed up. Okay, y equals mx plus p, right? This is your b, this is your intercept, and this is your slope that you're going to lock in, and this is each changing variable as it goes along. Okay, so now you can just double click that down, and these are all the predicted values for model 1. Now we can do the same thing for model 2. We're again going to take our intercept that we're going to lock in, and we're going to add our first coefficient that we're going to lock in. We're going to multiply that coefficient of water by the weekly return in water. And then we're going to add that to our second coefficient of sugar. We're going to lock that in. And we're going to multiply that coefficient by the weekly return of sugar. And that'll give us the predicted values for model 2. Very simple. Again, it might seem confusing with all the in-sample $ shit, but you're just building a basic linear formula and then a multiple linear formula. That's it. Super easy. So now the difference squared of model 1, it is exactly what it sounds like. You're going to take the return of Coke, subtract the predicted value of model 1, and square it to make sure it comes out positive, and double-click down. And then exactly the same thing for model 2. You're going to take the expected return for Coke, you're going to subtract the predicted value for model 2, and you're going to square it, and double-click down. So now we're ready to do our RMSE, which is exactly what it sounds like. It's the root mean squared error. So we just squared the errors here, right? Now what we're going to do is we're going to take the root mean. So we're going to take the square root, and we're going to take the square root of the average of model 1. Give it a couple parentheses, and we're going to take the square root of the average of model 2. And we can see that we want the lowest RMSE, so 0.01701, 0.01703. Model 1 has the lowest RMSE, so Model 1 is the winner. I believe there's also a class exercise that gives you more practice on this, as well as like optimizing in sample and out of sample testing, so I would definitely recommend doing that. This really isn't that complicated though. Again, you just build the linear formula based off of your coefficients, and then you're literally just calculating your error squared by subtracting the predicted value from the actual value, right? This is the predicted value, this is the actual value, and then squaring it. And then you're just taking the square root of the average of those squared errors in order to get your RMSE. And the lowest RMSE always wins.